subsurface of Venus. Keep going down inside Venus. Internal structure and tectonics. Well, tectonics, I already told you, they don't exist on Venus. Tectonics describes the large-scale motion of plates that make up the crust of a planet. You know, Earth's got plates that move around, and you know, plate tectonics, all that good stuff. It's long-term movement and monitoring. That's how you measure plate tectonics. It's very slow movement of plates. But scientists believe that Venus is just one big plate. It's just like, you know, plate, ting, 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 all around. There's no fault lines and stuff. So I'll put that there just to give you the definition of tectonics, but scientists believe there's no plates. However, if you want to go look for plates, if you want to prove the scientists wrong and find a fault line on Venus, that would be big news if you found a fault line on Venus. Okay, so internal structure. What is internal structure? Again, it's the structure of a planet that can be imaged or constructed. That's what they actually do. They construct it using seismic information from quakes or vibrations. And then this is how they do it on Earth. It's really cool. I think it's awesome. I had a planetary scientist to explain how this worked to me, and I was like, that's just so cool. I'm so glad we do that. I was impressed. Essentially, you measure vibrations from quakes and other things like high impacts or something. You know, if a meteor or something hits or if something falls, you know, you can just measure vibrations. But from these vibrations, you can tell what the inside looks like. Very cool stuff. So how do seismic waves images planets interior? So three-dimensional images of a planet's interior using seismic signals are generated by internal or external events, quakes, impacts, or tidal heating. Tidal heating doesn't occur on Venus or on Earth. Tidal heating is when you're lots of the moons of Jupiter and some of the moons of Saturn have tidal heating. Basically, it's the moons are so close that and the gravity of Jupiter is so high that it squishes the planet. So basically, if you think of the planet as a balloon, it gets squished one way and then squished the other way as it goes around. Jupiter, it creates lots of, has lots of moons that get squished a lot. And that constant squishing, just like when you fold a paperclip a lot, it gets hot, right? That's what tidal heating does. That constant squishing of a planet, or of a moon in most cases, creates tidal heating on the inside of the moon. So that's why some of the moons of Jupiter have hot cores on the inside, because Jupiter squishes them and squishes them and squishes them and squishes them. That's called tidal heating. It's not used in this case for Venus. I just wanted to include it because it's a way to measure internal structure. But quakes are the most common way to do it. Earthquakes, or in our case, Venus quakes would be the most common way to do it. So it generates a three-dimensional image by stacking 2D images, okay? It works like the opposite of a CAT scan machine. I don't know if y'all, it's not like, in a CAT scan, it's not we're taking a cat going over, that's like, meow, that's not a CAT scan machine. A CAT scan machine basically has an X-ray beam and energy source that sends signals to a receiver. You put a receiver in a single location, and the CAT scan machine has an energy source that moves around, okay? So the energy source that sends the beams through your leg or whatever you're scanning, it moves around, and then there's an imager that sits in one location, and it takes these images and stacks them up and makes a 3D image out, and it makes a 3D image out of the different images that it creates. It just cuts slices through, okay? And then it builds a 3D image from the slices, because it has in the case of a CAT scan machine, the X-ray beam or the energy source moves around, and the receiver, the film, stays in a single location. Now it's the exact opposite for earthquakes. There's one energy source. The quake is the energy source, but what we do is we have seismometers all over the planet, and those are the receivers. So one quake, multiple receivers, as opposed to multiple energy source locations in one receiver. So it's the exact opposite. Let's explain more. I'll keep going with this. It'll make sense in just a second. So the principles of seismometry: seismic waves, surface waves, compression waves, or compression waves are called P waves, and shear waves are called S waves that travel through the planet. Waves are generated together, but travel at different speeds. So when a quake happens, boom, there's a quake or some sort of seismic event right here at the North Pole. That's fortunate. And all those waves are created at that very moment in time. That's where those waves are created. And they travel through the planet. They travel through the planet at different speeds, okay? Some waves are faster than other waves. Some waves only go on the surface. Surface waves only go on the surface, for example. And And then as they pass through different materials, they travel differently also. And we'll talk about that. Stations close to the quake record the strong P and S waves and in quick succession. So the closer, the stronger the waves are, the further away, the weaker the waves. That's how we pinpoint where earthquakes happen and stuff, the epicenters of earthquakes. We use the seismic stations that we have all over the planet to do that. And the stations farther away record arrival of these waves after a few minutes, and the times between the arrival of those are greater. So, in a nutshell, an earthquake happens and it sends these waves through the planet, right? And you got the core, the mantle, you got the core, the outer core, the mantle, and the crust. Okay, so these waves go through the different materials, and the waves change as they go through different material. And so the seismic stations that are right here, the intensity of the waves are different than they were over here. Okay, the intensity and how the waves act are differently. Basically, I don't want to. I'm not trying to. I don't know much about this. I'll be honest with you. This is kind of what I know, but I also try to explain it so that it's easier to understand. Also, if you go through a liquid core, shear waves can't go through a liquid core. Only compression waves can. Only P waves can. So on the other side, if there's no S waves, if there's no shear waves, then it means that it went through some sort of liquid core on the inside because it stopped the shear waves. So that's how they know that. That's how we know that there's a liquid core inside Earth. We've never been inside there. That's really deep. But we've measured quakes, and we know that if a quake happens on one side of the planet, on the other side of the planet, you won't have any shear waves, but you'll have compression waves. That's how we did it. And we can draw a picture of the inside of a planet like that. Now, how does a seismometer work? I don't know. This is kind of looks like the old school. Y'all seen these on like old movies and stuff, right? A seismometer, the rolling paper or the old, just like people are like watching it and thinking just moves and then this is very old school. So in a nutshell, there's a mass that hangs from a spring, and then there's a rolling paper, okay? And then and the paper and the spring and this structure, this frame are fixed to the planet, fixed to the Earth. So if the Earth moves, this paper moves essentially. However, this mass is on a spring, so it doesn't move. So this thing moves up and down, and the pencil there, the pen rather, it creates these. The paper moves and the pen stays the same, so that's what creates those lines. That's kind of it in a nutshell. Now, this is a one-dimensional. If it shakes in this direction, if it shook in this direction, this guy wouldn't read it, right? Because it only has one direction. We've got three-dimensional seismometers that we use all the time. So if a quake happens, it can measure in all three dimensions, X, Y, and Z. And it can tell it can measure angles between the things. And the spring action is optimized for a specific frequency. We don't use these old school ones anymore. They're all digital basically nowadays. They're all internal, very small digital things. But kind of the old school. An accelerometer works very similarly. And all of you, whether you know it or not, are familiar with accelerometers because there's an accelerometer in every single smartphone. That's why you can, and even iPod touches and stuff. That's why you can play the games where you go like this, and that's why it knows if it's flat. It knows if you turn it. It knows the phone knows because there's an accelerometer on the inside that knows. So the accelerometer measures accelerations or changes in velocity. It measures if it does this. It knows if you're moving it. There's an acceleration that it feels like. Right now, my phone feels. It's getting pulled down at 1G. It's being accelerated toward the planet at 1G, even though it's just sitting there. It feels that 1G of acceleration. So it behaves, accelerometers, this is just a drawing of one, behaves like a damped mass spring, like a seismometer. That's how they behave. Now the commercial ones are electronic, they use piezo resistive and capacitive components. Relative position can be calculated and integrated from acceleration data. So what this says, relative position. So we're going to do some calculus. So I don't want to lose you. Do not go to sleep. If you measure acceleration, okay, from acceleration you can calculate velocity. And from velocity, you can calculate relative position, not absolute position, but relative position, meaning that my phone, let's just say this, my phone, if I were to do this to my phone, and my phone knows, because there's an accelerometer inside, if I were to turn it on and have it collect data, it would know that it just did that, okay? And it would know that it did this acceleration, and went over this arc right there, and it will be able to tell you, it can tell you the accelerations it experienced, and then from those accelerations you can calculate velocities, and from those velocities that it experienced, you can also calculate the position, the relative position. It will not be able to tell you, the accelerometer alone cannot tell you that it is in Huntsville, Alabama, and then is it at, these lat and long coordinates. It has now this happens to have a GPS inside. That's different. We can't think about GPS. GPS requires a network of satellites. We have no network of satellites at Venus, okay? So forget about GPS, all right? So, but an accelerometer can tell you, okay, the phone went that distance and over that distance in that time, so it can tell you where it went in a relative position. So if the phone knows where it is when it starts, if my phone says, okay, I know where I am right now, like on a spacecraft, if the spacecraft knows where, and our spacecraft know where they are in three-dimensional space because they've got sensors on board that know where they are. We'll explain that later. But so if your accelerometer, if my phone were dropped from a spacecraft, then it started collecting data and it hit the ground, my phone could measure accelerations and velocities and relative positions to where it hit the ground, and then from that data you could calculate where it ended up because you knew where it started. Because it only gives you relative position data, but if you know where it starts, then you can calculate where it ended. Does that make sense? We'll talk more about that later. But so an accelerometer is a really, really powerful device, a powerful instrument, and we use them a lot. We use them a lot in smartphones, but in InSPIRESS we use them too because they're cheap and they're light, which are two things that I really like. And also they can give you a lot of information. They can give you positional data, which you otherwise cannot get. So we'll talk more about this too in class. So issues with internal structure. Lots of issues with it, okay? It's hard to measure, but it is, scientists want to do we don't even know the internal structure of our own moon, by the way, just FYI. Internal structure is hard to do, but scientists want to measure internal structure for every planet in the solar system because we want to know what's going on inside these planets. Must have a network of accelerometers or seismometers, at least 3. You must have at least 3 different seismometers or accelerometers to get this, to make this thing work back here. To make this work, you have to have at least 3 locations, 3 different sensors across the planet. You can have them near each other, but then you can't tell the internal structure of the whole planet. So you need them across the planet, at least 3 across the planet. The sensors have to be in sync with one another. They have to know, because when the waves hit, it's not just, they have to know the difference in the time that the waves hit. They got to know all that. So that's an issue too. And when we're talking about living on Venus for only like 5 hours at the surface, it makes this really tough. Impact resistance, ability to withstand high G loads. Seismometers, not so good. Seismometers are more sensitive than accelerometers. They are better at measuring seismic activity. Don't get me wrong, seismometers are built for that. Accelerometers really aren't built for that, but accelerometers can measure seismic activity. They can measure the vibrations. Seismometers are just a little bit better. But an accelerometer can withstand really, really high Gs. We have accelerometers and lots of missiles that we launch. And nowadays we've gotten to where we like for missiles not to hit the ground and explode. We want the missile to hit the ground and go like 10 meters deep and then explode. So these accelerometers withstand thousands and thousands of Gs. And they can still live. When the bomb blows up, then they blow up. But still, accelerometers are very robust. So accelerometers can also calculate position, which seismometers cannot. Orientation on the surface. If you don't have a 3-dimensional accelerometer or seismometer, then you have to make sure the orientation is proper on the surface. So therefore, I would recommend using a three-dimensional accelerometer or seismometer. I mean, there's a 3D accelerometer in your phone. So they're very small. There's probably 2 of them in here just as a backup. The distance from the lander, if you're measuring internal structure, you need to get away from the lander. Landers are basically make a lot of noise. They pop and crackle and they snap and crackle and pop and all sorts of stuff. Because things heat up and cool down, and it's this metal and it expands and contracts and stuff like that. So landers are noisy. Okay, so you need to get away from the lander. We have on our moon, on Earth's moon, we've got we have the Apollo missions, and they put seismometers down, but they put them right next to the landers. And so every time the sun comes up on the moon, the lander heats up and it heats up, and then it crackles and pops, and then when the sun goes down, it cools down and cracks and pops again. Drives the scientists crazy. I've talked to a few of them. They're like, oh, we can't, because they see all the data, all the crackling and all the vibrations from the lander in their data. Drives them crazy. So you need to get away from the lander. 100 meters is the minimum. How long do you operate for the network? That's a big issue on Venus, because how long can you survive? And then power, communication, thermal, and all that. Thermal is going to be a big issue for Venus, and so is structure, because the pressure is so high. Okay, so how do you create a seismic network? If you want to look at internal structure, how do you create this seismic network that we've been talking about? There's 2 basic ways to create a network on the planet. You can either penetrate the surface. You can have something that goes down and punctures into the planet and actually goes below the surface of the planet, or you can have something that remains on the surface. You can have something that lands and just kind of skips across the surface and then rests on the surface of the planet. So now bear in mind, the lander is only one single point, okay? And so you want to have points that are, half the planet away from you. And so you can't just be next to the lander. You can't just go deploy from the lander. So it means you're probably going to be deploying something from an altitude. That means that you're going to have something that probably falls off of the balloon or the orbiter. So if you want to penetrate the surface and go have something that there's smacks and goes below the surface, there's the positives or better connection with the ground. If the ground moves, you will move. Radiation shielding, not much of an issue on Venus actually, and you're more position and certainty. You're not going to bounce around, and also the wind won't blow you around like the wind would blow you around if you were just on the surface. The negatives, high impact loads. That's the big one. When you hit the ground, it's gonna hurt. You're surrounded by the soil. If the soil, in this case, the soil of Venus is going to be very hot, so it'll make your probe a lot hotter. If you're on a cold planet, it'll make you cold. So, but in any case, you'll be surrounded by the soil or surrounded by whatever. Possible communication issues because you'll be underneath the surface. You'll have dirt over your head, and so you might not be able to send signals through the dirt. And then your impact angle, you got to make sure it's right, or you won't, or you'll just skip, or you might just do something funky. If you remain on the surface, the positives are lower impact. It's gonna skip across the ground, but it's not gonna experience this boom. It won't hurt as much basically as if you were to strike the ground. You're not surrounded by the soil, and so in Venus's case, it might not matter much because it's so hot at the surface anyway. The atmosphere is. Better overhead communication because there's no soil above your head. The negatives are it's poor connection to the ground. If the ground shakes, you might not shake as much as if you would if you were part of the ground, because you might just be a ball, or you might not shake as much as you would. Less position certainty, especially on Venus. I mean, you're going to hit the ground and skip around, and that gives you position uncertainty. But on Venus, you could also get blown by the wind, and if your accelerometer moves around like that, that might cause an issue. Surface features will cause a problem if there's gullies and hills and stuff, and then more exposure on the surface. So this is a really great drawing of basically this is penetrating the surface. You fall from the orbiter or the balloon or whatever, you just go smack, and you just go right and stick it in the surface. And then you remain on the surface, you go bounce, 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 bounce. That's basically the 2 ways to do the seismic network, to have something fall from orbit. This is basically, if you're falling from orbit, this is kind of the 2 ways to do it. Or if you're falling from the balloon too, this is kind of the 2 ways to do it. You can either stick in the ground or you can bounce until you come to rest. Oh, so temperature and heat flow. We're almost done. Don't worry. Temperature and heat flow. What are temperature and heat flow? What are we talking about here? So temperature measurements. The objective are to understand the thermal environment of the surface of Venus. Okay. So usually at many points, when I say temperature measurements, I see like, okay, what's the temperature here? What's the here? What's the here? What's the temperature here? Temperature here? Temperature over here? Okay, what are the temperatures there? Compare temperatures over a variety, like temperature measurements, as many as you can afford all over the planet. That's temperature measurements. Okay. Heat flow, on the other hand, heat flow is very detailed, but at a single location. Temperature measurements are scattered around. You know, here, 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 here. Heat flow measurements are if you were to bore, like stick something in my ear and say, what's the temperature difference as you go outside my ear, as you from the inside of my brain out to my ear. That's kind of gross, sorry, I guess. But anyway, you get the point, right? Heat flow is a single location, maybe two locations if you can afford it, but you actually have something that goes below the surface of Venus, and you measure temperature at different locations from the depth all the way to the surface. And that's called heat flow because you can see the difference in the temperature as you go deeper. And that's basically temperature versus heat flow. Temperature are surface measurements scattered about, and it's a overall world view. Heat flow is a very detailed view of one single location. You're going down and you're going deep with that single location. That's basically what it says there. Temperature network. Scientists believe that Venus is basically isothermal. They think that it's kind of the same temperature all over the place. That's what they measured from orbit and whatnot. There are hot spots on Venus. They don't know why there are hot spots. They think they're from volcanoes or from concentrations of something, but they don't know why. And so what are the actual temperatures on the surface? The Russians measured some temperatures down there, but mainly they just took pictures. They just wanted to prove they went there. What is the real temperature variation? These are actual temperature, from orbit probes of Venus's temperature, and you can see there's hot spots, there's cold spots and stuff. There's not much of a difference between these temperatures, but why is there a variation? What causes these hot spots that they have, and do the hot spots change? Do the temperatures change in a location? You can measure the temperature over time, and that gives you some different things as well. Don't forget about, with all these measurements, there's a time component as well. The same temperature, like if you were to measure the temperature of Huntsville, Alabama, over the course of a year, it changes drastically. And so I'm sure it does the same on Venus as well. Not as drastic, but I'm sure it'll change. And so you could check the poles versus the equator temperatures, and what are the causes of the hot spots. So temperature network, again, the probes are out on the surface. It's a network of probes. You want to get basically it's kind of like, just basically think of like a shotgun approach to temperature probes. Just a bunch of them, as many as you can fit. And the farther apart the better, the more the better. It gives a better variety. Unless you want to concentrate on a specific region of Venus, that's different then. This implies that some of them will probably fall from an altitude, just like before. So if they fall from an altitude. Heat flow. Again, another great drawing. Heat flow, like I said, you're going to measure the temperature at the surface and then at intervals as you go down. And you want to get as deep as possible, and you want to measure as many intervals as possible. The main things you want to know, though, you want to be able to, is you don't necessarily have to know what this bottom location is, because if you have something that hits the ground, you might not be able to control how deep it goes. But you want to be able to know, you have to know how far apart these temperature readings are, okay? That's very important. These dy, delta y, the difference in this distance here, you have to know that. And you want to know it very precisely, because that's how the temperature changes as you go deeper. And that's what you want to know, is that difference in that depth change, the temperature as it changes in depth. Temperature measurements on its surface to a depth below. The deeper the better, and the more the better, obviously. And the distance between each temperature measurement must be known. And also, getting to a depth requires energy. So how do you get to a depth? There's basically 3 ways to get to depth, and we'll not go into the positives and negatives for these. I'll just tell you about the ways. There's something called the DLR mole. It's a miniature pile driver, and the pile driver basically has a mast that goes up and then falls, up and falls, up and falls. You've seen them when they make bridges. That's a pile driver. It's not just a wrestling move. It's actually a thing. And up and fall, up and fall. That's a pile driver. They've got a miniature pile driver called the DLR Mole. DLR stands for Deutsche Luft- und Raumschaft. It's a German thing, and German air and space. The Mole is it's a miniature pile driver. It was designed for either Mars or the Moon. I don't know how well it would fare on Venus because Venus is so hot, but it's made to dig down. It's made for heat flow. You could use a drill similar to on Earth. Drills are heavy and big and require lots of power. Also, drills require mass. Have you ever seen a small person, try to use a drill and it goes zzz, and kicks their arm back, because you have to hold the drill steady or then it wants to spin the other way on the top. So drills require mass. And then a penetrator, that's just having a sharp, like a missile, basically go shpunk and hit the ground. And that's a penetrator. And we've had lots of NASA missions. We've never actually had a penetrator mission that was successful. We've had lots of missions that were planned that way. And the most popular one is actually the Japanese mission called Lunar A that was planned for the moon. Going to be a penetrator mission on the moon. If you want to know more about that, just let me know. So if you're going to look at heat flow, how do you get to your depth? These are basically the 3 ways to do it. Thermocouples. With heat flow or with temperature measurements, you're basically going to use a thermocouple. That's how you measure temperature. Thermocouples are how we measure temperature in the lab or on spacecraft. We don't just use a thermometer like a temporal scanner or a mercury thermometer. Those don't work. We use a thermocouple because they're more reliable. And thermocouple, okay? Couple to thermotemperature. So as the name would suggest, it's 2 things. A thermocouple, the book definition is 2 dissimilar metals that are basically sandwiched together. So you have 2 different metals, okay? And then if you have these 2 metals and they're sandwiched together with something in between, and you heat them or you cool them, what's going to happen? Right, yes. They will expand or contract, and because the metals are different, they will expand or contract at different rates. And so what's going to happen is the thermocouple will do this, or it'll do that, or something like that. That's what the thermocouple is going to do. It's going to expand or contract at different rates. And this bending, this expansion or contraction of the 2 different metals, what it does is it induces a voltage between the 2 metals because of the way they're joined. So a voltage, this thing expands and it induces a voltage, and the voltage, this is connected to a computer. It's just a wire connected to a computer. And the computer measures the voltage, and then it says, 42 degrees. Sweet. And so that's how it works. So you can they're calibrated and stuff. Thermocouples, extremely robust. Basically, it's just 2 wires. They don't require power, really. They actually create a little bit of power, but they don't require power to operate. The computer itself requires power. Whatever is reading the measurement requires power, but the thermocouple itself does not require power, which is a bonus. Pressure transducers operate very similarly also. So very robust. I mean, we put thermocouples on everything, on the outsides of planes even. So robust, thermocouples, and it's basically 2 wires, very light and robust, awesome instrument. Temperature issues with temperature and heat flow, you got to have good contact. Temperature is touchy, and you got to have good contact with whatever you're measuring. You want to make sure that you're touching it and you're not touching something that there's not a small gap, okay? That's the big deal. Time and location, it does no good. If someone says, what's the temperature today? And I say, it's 10 degrees. And they go, well, where is it 10 degrees? I'm not telling you where it's 10 degrees. It's 10 degrees somewhere. So you need to know where the location. When you measure temperature, you have to have a location with that. Even if you're falling through the atmosphere, it does no good to measure temperature if you don't know your location. And that's where the accelerometers will come into play, is that you can measure relative position as you descend with the accelerometer. Accelerometer's taking data, and then you're taking temperature data as well, and then later someone calculates where that position was based on the fixed position where everything started, okay? We'll talk more about that, but you can't take any measurement without positional data because it does no good whatsoever. You have to have positional data because you have to know where the measurement was taken, okay? Lander will influence measurements. Lander and the balloon will also influence measurements, and the orbiter will influence measurements. So you want to get away from the different elements. We're going to make you get away anyway, but you want to be away enough that these guys won't influence the temperature measurements. Thermocouples are just like the thermometer that you use to measure your temperature, like when you're sick, is awesome at measuring between you know, like 80 degrees Fahrenheit and 120 degrees Fahrenheit, because outside of that range you're dead and they don't care. So, but it's not great at measuring the temperature if you wanted to cook a steak or something, because it's not made to measure that high. So you want to find a thermocouple that measures in the range that you think you're going to see. If you're going to be in the upper atmosphere of Venus, it's much cooler than near the surface of Venus, okay? By hundreds and hundreds of degrees, it's much cooler. So you want to make sure you know where you're going to measure. They make some thermocouples that'll measure a wide range, but their precision's not that great. So you can combine. You can have some that measure different bands, and you have some that measure wide ranges and stuff like that, and you can get the best of both worlds that way. Watch out for thermal shorts. A thermal short, it's not a short person that, you know, it's not like short, you know, thermals or something. But a thermal short is what it sounds like. Like this is a piece of metal right here in my hand. If I put a hot thing here and a cold thing there, the temperature is going to conduct through this metal. And if I want to measure something, I need to know if, well, let's just say this is my penetrator. I'm going to say this is my penetrator, and if I have and I put thermocouples along the walls of this penetrator, and the outside of the penetrator is made of metal, the entire outside of the penetrator is going to be the same temperature after a while, because metal conducts heat. And so that's a thermal short. Basically, you've created a short across the entire penetrator because it's a metal and because metal conducts heat. And so you want to watch out for thermal shorts. We'll talk about that as your designs mature. Magnetic fields, again, scientists don't believe that Venus, or let's just say this, we've never measured Venus's own internal magnetic field before. It might exist, but we just never measured it. I wanted to include this because scientists don't know why there isn't a magnetic field, I guess is the best way to say it too. So I think some scientists probably believe there is one. But magnetic field is measured, it's usually called B field, it's the B with the vector on top. And it's produced by moving electric charges. And like in the case of Earth, we've got a big rotating magma core, and it creates a magnetic field for us. Magnetic measurements, they're usually, there's a magnetic field is a vector, okay? And some of y'all, I'm sure y'all studied vectors before in physics and stuff. A vector has, and just like the bad guy from Despicable Me, the first one, a vector has magnitude and direction. So a magnetic field has magnitude and direction, and you can measure you can measure the vector magnetic field, or you can just measure the scalar magnetic field. The scalar, just the magnitude of the magnetic field. You don't know the direction of it. Most times you want to have both the magnitude and the direction. Flux gate magnetometers are the most popular. They're light, they're simple, and they work great. So if you're looking for a magnetic field measurement, look at a flux gate magnetometer. Very easy to use. It's a 2-coil thing. One coil is excited with an alternating current. The other coil just sits there and listens. So basically, it sets up its own magnetic field inside this. This is the one right here. It sets up its own magnetic field, and the other coil just monitors the magnetic field set up by this one. And if this magnetic field gets perturbed, then it knows there's another magnetic field out there somewhere. That's how these things work. And then isolation requirements, big deal. Magnetometers are awesome, but the problem is they measure all magnetic fields. So if you're near the lander or near the orbiter or near the balloon, near anything electronic, you're going to measure the magnetic field of that electronic device. So you have to get away. When we put magnetometers on spacecraft, we put them on 10-meter booms. And then we put 2 of them on there. We put a magnetometer at the end of the boom, and then we also put a magnetometer at the base of the boom. So we want the magnetometer so far away from all the spacecraft junk that creates its own magnetic field. We don't want to measure the magnetic field of the spacecraft. We want to measure the magnetic field of the planet that we're at. Okay, so that's a big deal. The isolation requirement for magnetometers is huge. Magnetometers usually sense continuously for their lifetime. It's kind of an instrument you don't turn off really, because of their changing nature. So what's next? You guys, your team, work with your team, work with your teacher, work with me and PJ to choose your science objective. We'll help you talk through some things if you want to talk through some ideas and stuff, whatever. What are you interested in? what interests you about this region or area. So first look at, okay, are we interested in a certain region or area of Venus? Are we interested in the outside, the atmosphere, the surface, or the inside? What region are we interested in? What interests us about that region, and kind of narrow it down from there. I mean, if you find one that you just say, yeah, that's it, we're going with that one, sweet. But if you have to talk it through with your team, you can talk it through this way. Start what interests you first, and why does it interest you, and you can build from there. Research the environmental conditions associated with your objective. If you are in the upper atmosphere of Venus, it is very different than the surface of Venus. Okay, extreme hundreds and hundreds of degrees difference, and hundreds of psi, thousands of psi difference between upper atmosphere and lower atmosphere. I mean, it's crazy difference. So whatever your objective is from here is going to define your environment there. So make sure that don't let it scare you away. Don't get me wrong. I mean, you can accomplish anything in this, but once you find your objective, then you make sure your environment is defined by that objective. Start thinking about instruments that you're going to need. I went over some instruments in this thing today. We'll talk more about instruments later. Here's the Science Trace Matrix, and I chose internal structure because it's a good example. But the Science Trace Matrix, basically, you start with your objective. You have your measurement objective. Here's your science objective first, and then what are you actually measuring is the second one. The measurement requirements, what are requirements on that measurement, and then what instrument are you going to use, okay? So if you want to measure if you want to determine the internal structure of a planet, that's our science objective. Well, let's just say we want to do that. So that's internal structure is our science objective. What are we actually measuring? We're not actually, there's no such thing as an internal structometer. There's nothing, it doesn't exist, right? We're actually measuring the quakes, the vibrations that the planet makes, and it's going to shake. The planet's going to shake, we're going to measure that, okay? What are the requirements on this measurement? I just said we're going to have at least 3 probes, because we have to have 3 to make up this network. They're going to stay on the surface. That was just a decision we made. 4 hours lifetime, because Venus is pretty nasty place. We're going to hope we get some quakes in there, and they're going to continuously measure during those 4 hours. What are we going to use for that? What instrument we're going to use? We're going to use an accelerometer. It's going to sit there and just measure for 4 hours. Then it's probably going to melt or something. So that's the Science Traceability Matrix. And then after this, we'll go into there's the instrument matrix, where you look at that instrument and you say, how much power does it require? What's its mass? Blah, 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 blah. That's later. But so what's next? Work on your science objective. Talk with your team. Talk with your teacher. Talk with us. We'll help you with it. Let us know how we can do this, and we get through this. Whatever you're interested in, let's go for it, okay? We may have to back off some of what you think. If you're too grandiose, we'll tell you, hey, maybe scale it down just a bit. Also, again, if you want to come up with something that I did not talk about today, that's fine. If you want to come up with your own objective, that's fine. But let us know. We'll talk it through to make sure that that you've developed it, okay? Because you want to have kind of have it fleshed out. But that's it. Thanks for watching. I hope this wasn't too long, and see you in class. Bye-bye.